Why are transfer functions crucial for control systems? Have you ever wondered how engineers manage to control complex systems with precision? One of the key tools they use is the transfer function. So, why are transfer functions so important for control systems? Let's break it down. In electrical engineering, a transfer function is a mathematical model that connects the output of a system to its input. This connection is made in the Laplace transform domain. By using transfer functions, engineers can simplify the analysis of dynamic systems. Instead of dealing with complicated differential equations, they can convert these equations into algebraic forms that are much easier to work with. A transfer function represents how a system responds to any input signal, assuming the system behaves linearly and does not change over time. It is expressed as the ratio of the Laplace transform of the output to the Laplace transform of the input. This ratio shows how the system alters the amplitude and phase of input signals at different frequencies. One of the main advantages of transfer functions is that they help characterize system behavior. Engineers can analyze how systems respond over time, including both transient and steady-state behavior. By looking at poles and zeros, which are values that make the function infinite or zero, they can assess system stability and performance. Another benefit is that transfer functions allow for simplified mathematical treatment. By working in the Laplace domain, engineers can turn complex time-domain differential equations into straightforward algebraic expressions. This makes it easier to design and analyze control strategies without needing to solve complicated equations directly. Transfer functions also play a vital role in frequency response analysis. They describe how a system reacts to sinusoidal inputs at various frequencies. This is essential for designing filters, amplifiers, and feedback controllers in electrical circuits. Moreover, transfer functions enable a modular representation of systems. Complex systems can be broken down into smaller subsystems, each represented by its own transfer function. This modular approach, often visualized with block diagrams, makes it easier to analyze and design large-scale control systems efficiently. When it comes to stability and control design, transfer functions provide tools to evaluate system stability using methods like the Routh-Hurwitz test or Nyquist plots. They also assist in controller design methods, such as proportional integral derivative tuning, by linking controller parameters to system response characteristics. In practical applications, transfer functions are fundamental in designing and analyzing circuits, including amplifiers, filters, and feedback control loops in motors or power systems. They help predict how these systems will behave under different input conditions and guide adjustments to meet performance specifications. In summary, transfer functions are an essential tool in electrical engineering. They help model, analyze, and design control systems by capturing dynamic properties in a mathematically manageable form. Understanding transfer functions is key to mastering control systems and ensuring they operate effectively.